Alrighty, in this video we are looking at natural logarithms. These are a unique category of logarithms. So let's get started. Our objectives are to calculate the values of natural logs and to use natural logs to solve exponential and logarithmic equations. So let's begin with just a letter that actually we know to be a numerical value. When you think of that letter right there, that Greek letter, we know that it is pi. And pi is not just a letter, it's actually a very unique number. We know that pi is the circumference divided by the diameter of a circle. And a lot of times we say that it's about 3.14. Now we know that that actually is just an approximation. That decimal continues on forever and ever and ever and ever. And there's no pattern to it. It doesn't ever repeat itself. So it's what we call an irrational number. It falls into the category of numbers including like square root of 2 as well. And we're actually going to learn about another letter that is also a number. So let's go. The number E. It's often called the natural base, and you'll see shortly why that is. And it was discovered in about the 17th or 18th century. But I'm not going to just tell you what the number E is equal to, so hang in there for a little bit longer. In about in the early 1700s was born a gentleman named Euler. A lot of people say his name to be Euler in our part of the country, but it's actually Euler. And he was working with this number, and he's often called the one whom E gets its name from. It's sometimes called Euler's number, and because he worked with it so much. But there are some really funny stories that say that the number E got its name because his first name is E, but there's really no fact to that. But really there was someone before him that did more work with it that we want to look at. And his name was Jacob Bernoulli, and kind of a stoic looking man, right? He was alive a little bit before Euler was, and he is often credited with actually discovering E, even though Euler is maybe more popular. He was investigating the mathematics of finance, which, yes, ladies and gentlemen, talking money. He was looking at, in particular, compound interest, which we've studied. You've seen this formula used to determine interest of an investment over time, where remember, P is what you start with, the principal, R is your rate, N is the number of times it's compounded, and T is the number of years. And his curiosity was, if I take N and I just make it larger and larger and larger so that it's compounding faster and faster and faster, will I just keep growing my investment, or what's going to happen there? And so why don't we look a little bit at the work he actually did. He took that formula and he tried to kind of make it a little bit simpler for himself to work with the numerical part here. For P, he let P be 1, he let the rate be 1, and he let time be 1, so that his computation could be done easier, and you'll appreciate him for that in just a moment. And here it is. So this was the problem he was working with, and he was seeing as N gets larger and larger and larger and larger and larger, like almost to infinity, what happens? And what he found is that it doesn't just keep growing, shockingly. It actually reaches a point where it's not growing much at all. at all. Yeah, at first it grows crazy fast, but then it reaches a point where it's approaching this number, and we call that, when it's approaching something, its limit. So there was a limit to how much could actually be earned, and that limit number is what the number we know to be E. But I'm still not going to tell you what E is. You're actually going to figure it out, and we're going to do that by using this formula. And we're going to go way out there. We're going to go out to 1,000,000 and see what that is, and it'll help you to find out what that value is. So I want you to pause this video, plug in those numbers, and complete the table so that you can see what it is that E, the value of E is. What is our formula growing up to? Okay, so if you plug in 1, the output would have been 2. If you plugged in 2, it would be 2.25. If you plugged in 10, it's 2.59374. Now, let's jump big number here. 100,000, it is not a significant difference. 2.71827. Not a huge change there. And then watch what happens. When you go to 1,000,000, it is nearly identical. I mean, look at that. All that changes, I mean, it's such a small amount. It was 2.71827, and then it was 2.71828. I mean, that is barely any change. And so you can continue like that. But what you're going to find is that approximately E is that value. It is 2.71828, and there might be just a little bonus on quiz or something like that, where if you have that memorized, then you can earn some bonus. So let's continue on here. We're going to actually use that E value. When we're talking about natural log functions, the inverse of the exponential function, which would be y equals e to the x. So there's that e value to the x, exponential. That inverse of that would be the natural logarithmic function. And that would be a base of e, log base of e to the x equals y. But what's really cool here is because this is used so often, we can abbreviate log base e as just ln, which is the natural log. All right, so why don't we actually use these tools to solve some problems.